So here again you can write fraud number. Okay, g square by gd. Here you can write vy root over gd whole square. Okay, this is nothing but our fr2, fraud number square. Okay, fraud number square. So in place of this q square t by ga cube, you can write fr square. So here at equation 2 you can also write like this: dy by dx is equal to sb minus sf divided by 1 minus fr square, and put it as equation number 3. So that whatever you have got the equation number 2, that is a general equation. So you can consider the channel is rectangular, or you can say wide rectangular, where is r equal to y. Your hydraulic mean depth is equal to depth of flow. Okay, so you can substitute those things here using this your dynamic equation. Okay, this is our general dynamic equation. Dy by dx is equal to sb. We have taken common here. It's up to you which expression you want to use. Okay, the same thing. And then again q square t by ga cube, you can modify it by using this condition wide rectangular, and you will get some expression, and you can substitute here later on. Okay, so depending on this shape and condition, you again modify your dynamic equation. Depends on you. Okay, suppose for wide rectangular you have q square t by ga cube. Here it's a rectangular channel and it's wide. This is the level of water. Okay, so here in place of top width, this is our top width. For rectangular channel, your top width and bottom width will be same. Top width and bottom width will be same. So we can write in place of top width, we can write b. Okay, divided by g area. Again, it's b into y. Okay, for a rectangular channel, your area is b into y. So b square into, sorry, b cube into a cube. Okay, then again you have q square. So this b and here one b will be cancelled out. So we'll get g b square y cube. G b square y cube. Again your small q, discharge per unit width, a small q. So in place here q square and b square, you can write small q square, g y cube. This is nothing but your yc for a rectangular channel. Yc is q square by g. Okay, so remember yc is q square by g to the power 1 by 3, to the power 1 by 3, to the power 1 by 3. So yc is equal to q square by g to the power 1 by 3, or you can write yc cube, yc cube divided by y cube. Okay, so you can write yc by y whole cube, and you can substitute here q square t by ga cube. Okay, so now then again we use our Manning's equation. This is equal to area into velocity. For velocity we use Manning's equation, 1 by n r to the power 2 by 3 s to the power half. Okay, so here again r for wide rectangular, we consider r is equal to y, so it will be y to the power 2 by 3. In place of r we are going to substitute y value. Okay, This is discharge is equal to a by n y to the power 2 by 3 s f to the power half. Okay, for equation number 5. When the flow is uniform, because in the assumption you have seen, we have considering the flow is an uniform, your y equal to yn and sf to be equal to sb. For uniform flow, all the depths are same and your slope is also same. Okay, so we'll substitute here in equation number 5. Okay, this is equal to area into b into yn divided by n, that is Manning's n, y to the power 2 by 3 sb to the power half. Okay, so the q will be your b by n. Okay, and this will be with addition, because yn multiplied by yn to the power 2 by 3, it will be 5 by 3 sb to the power half, 6. Okay, so now we have to divide this equation 5 and 6. So you'll get q by q, and if you divide this equation, okay, this is 5 and this is 6. Divide equation 5, divide equation 6. So this q will cancel out, it will be 1, and what will be left out? Okay, so you will get all the cancel outs, to a by b, 1 by y to the power 2 by 3 and root over sf divided by sb. Okay, finally we get an expression for sf by sb. Okay, just write down the steps. Okay, this is a simple mathematics, you can easily understand this thing. If you don't, then you just ask me in the next class. Okay, simple mathematics, we have to just divide both the equation. Okay, and you will get a value for sf divided by sb, and I'll tell you why we need this expression for sf divided by sb for y rectangular. over. Yes, so the next, yes. So see, in the very beginning, we have the dynamic equation dy by dx sb equal to 1 minus sf divided by sb. So in place of that sf divided by sb, we are going to substitute that expression what we have derived just now for wide rectangle. Okay, and for q squared t by ga cube, we are going to substitute this expression. Okay, just to simplify the calculation. Okay, so you can see here. Okay, so sb divided by sf 3 per half. Okay, they got one expression, and then finally they got this expression. Okay, y by yn to the power 10 by 3, and that expression we are going to substitute here, yn by yn by y 10 to the power 3, and here again yc by y to the power 3. Okay, so for a wide rectangular, if I ask you to find out change in depth with respect to distance, that is dy by dx, you can directly use this expression. Or similarly, you can derive an expression for other shape also, like trapezoidal, like triangular shape, or any kind of shape. Okay, we can simplify the equation. Okay, simply by providing the depth and base slope, we can directly find out the dy by dx. Okay, so we'll solve few numericals related to gradually varied flow. Okay, okay, before that we will see that the gradually varied flow equation we cannot solve manually. Okay, so we have to use some methods to solve that gradually varied flow or dynamic equation of gradually varied flow. Okay, so you can this is not in your syllabus, or I think this that direct step method is there in your syllabus. Okay, let's see, we'll try to solve one method, to solve gradually varied flow equation using one method. Okay, but those are not much important in your syllabus, because when you go for master degree you used to do all this thing. Okay, so here, but you should know the methods. What are the methods we are going to use for solving that gradually varied flow equation? Okay, one is direct step method, second is your modified step method, then next one is your graphical integration method, fourth is integration with the help of varied flow function, and fifth one is numerical integration method. So you just write down the methods to solve your gradually varied flow. These are the methods, mathematical methods that you use for solving your dynamic equation of gradually varied flow. Okay, so you just write down the methods. Okay, we'll see, if possible, if time permits, we'll solve one numericals using one method, so that you will get a hands-on training with this, how to solve a gradually varied flow. You just write down the methods. over. Okay, so next topic you write that classification of channel bed slope. Okay, this is the next topic, classification of channel bed slopes. So number one is your critical slope, SC. SC is nothing but your critical slope. Okay, S is for slope, C is for critical slope. So what is critical slope? This is nothing but for a given discharge. For a given discharge and channel shape, critical depth YC of flow exists. Okay. So for this known critical depth, for this particular critical depth, if you want to find out the slope corresponding to that particular critical depth, that slope is called critical slope. Okay. So critical slope is nothing but slope at critical depth. Okay. Slope at critical depth is denoted by SC, and hence in this situation your bed slope is nothing but your critical slope. Okay, and your normal depth is equal to YC, is your normal depth is equal to critical depth. So the depth of flow is critical at this time, and if you find out the slope, that is called your critical slope. Okay, next is your mild slope. So this mild slope is when your bottom slope SB is less than the critical slope. When your bed slope is less than your critical slope, that is your SB is less than SC, the slope is called mild. Okay, so in critical slope your SB is equal to SC, it's same. If it is less than SC, then it's called mild. Okay, if it is greater than SC, it's stiff. So your bed slope, if it is same as your critical slope, then we can say that the slope is mild, sorry, critical slope. If your bed slope is less than the critical slope, then you can say the slope is mild. Okay, if it is greater than critical slope, then you can say that slope is steep slope. Okay, so here also your normal depth is mild. In mild your normal depth is greater than critical depth, and your third steep slope, your normal depth is less than critical slope. Okay, fourth one is horizontal slope. When channel bottom slope is 0, that is your SB equal to 0, then we can say the slope is horizontal slope. Okay, and your depth of flow will be normal depth of flow is in infinity. Okay, or horizontal slope. And one is your adverse slope, that is negative. When your base slope is in negative, then we can say that your slope is adverse slope and your normal depth is imaginary or not existent. Okay, you can say that slope is less than 0, that is your negative. You can say that yn is imaginary, that is not existent. Okay, so these are the slopes we have. One is critical slope, mild slope, steep slope, horizontal slope, adverse slope. Okay. In critical slope, your SB is equal to SC and your normal depth is equal to critical depth. Mild slope, when your bed slope is less than critical slope, then we can say the slope is mild. Okay. And your yn value, that is normal depth, is greater than your yc value, that is your critical depth. For steep slope, if your bed slope is greater than your critical slope, then you can say this slope is steep and your normal depth is less than yc value. Okay. Horizontal slope, your slope is bed slope is 0 and your yn is infinity. Adverse slope, when your bed slope is less than 0, that is in negative, so there will be an adverse or negative bed and your yn is imaginary or not existent. Okay. So these are the slopes, and based on the slopes we have some profiles. Okay. So those profiles we are going to discuss in the next class. Okay. So this is almost the end part of this gradually varied flow. Once you find out the profile, then there will be some numericals related to this profile. Okay. We will solve few numericals and then we will go to or move on to hydraulic jump, that is your rapidly varied flow. Okay. In gradually varied flow, we need to study about what is gradually varied flow. Then we have the dynamic equation for gradually varied flow, and the last part is the profiles. Okay. And we'll see, if time permits, we'll go for solving one dynamic equation, that gradually varied flow equation, using one method, computational method. Okay. Those but it's not in a syllabus, but still we'll try. Okay. If possible, then we'll solve one. Okay. So thank you, students. Today we am going to end this lecture here. In next class we are going to continue with this classification of surface profile. Okay. So based on these slopes we have some profiles, as we are going to discuss in the next class.